Okay, let's do some integrals by substitution. Sometimes this is called U-substitution because we use the letter U. I don't know why, it's just a long-standing convention. For this first one, we'll let u equal x squared, and then we'll take the derivative of that and get du is equal to 2x dx. And if we just rearrange that, we can target that x dx in the integral to make that 1/2 du. So that's what we'll substitute in for x dx. And then secant squared of x squared is just going to become secant squared of u. And now we can write out our new integral. It's going to be 1/2, that comes from the 1/2 du, the integral of secant squared u du, which we recognize as just tangent of u. So we'll just rewrite that integral now, resubstituting x squared back in for u because we're done with u now. So this is 1/2 tangent of x squared plus the constant of integration, and don't forget that. So the last thing we should probably do with an integral like this is just take the derivative of our answer and make sure we get the integrand back. So we're taking the derivative of our answer, and it's this is just a chain rule integral 1/2 tangent secant squared of x squared times 2x, and you can see that everything cancels out to give us our integrand back. So that's great. On to our second integral. Now this is a pattern that comes up sometimes, and because we don't have any x squareds in the denominator, we just let u equal the whole denominator. Then du is just going to be 2 dx, and then dx is just 1/2 du. And we end up with an integral that's just going to give us a logarithmic answer. So that sort of makes sense when you have everything in your integrand really just in the denominator. So it's 1/2 integral du over u, which is just 1/2 log of u plus our constant of integration. And then we just resubstitute 2x minus 9 for u, and there's our integral. Okay, here again, let's just take the derivative of that to make sure, and I'll just speed this one up a bit. But you can see that we take the derivative, use the chain rule, and we get our integrand back, 1 over 2x minus 9. By the way, sometimes I notice that my students forget that dx over 2x minus 9 is really just dx times 1 over 2x minus 9, or dx over 1. So don't forget that, okay? It helps to simplify these things. Okay, last integral. Now in these cases with trig functions, it's often best to target the trig function that's raised to the highest power and see if that helps. Remember that sometimes u-substitution doesn't help. But in this case, making u equal cosine x, which makes du equal to minus sine x dx, works pretty well. So we can just rewrite this integral as minus the integral du over u squared, which we should rewrite just to help us use the power rule as u to the minus 2 du. Well, then that's a pretty straightforward integral to do. It's just u to the minus 1 over minus 1. So we have a bunch of signs here to deal with, so just be careful with that. These two negative signs disappear, leaving us with just 1 over u plus c. So we'll just resubstitute cosine x in for u, and we can write that out. And then finally, take that derivative again and make sure that it gives us back the integrand. Yep, terrific, all done.